Let's ask ourselves what happens. Suppose we have a coil. We have a current in the coil. There's a magnetic field in the coil. And now what we want to do is ask ourselves, how much energy does it take to make our coil, turn this current I from 0 at time t equals 0 to some value I of t at time t. Now, the issue here is if we try to turn, if at t equals 0, there's no current in this coil, and we try to turn on the current, it's not going to go immediately up to its final value, whatever the source is that's generating the current, because there's a back EMF. Now, that back EMF you can think of as a voltage. And in order to drive this current, I have to oppose that back EMF, and the power that's associated with that back EMF that I have to oppose is that EMF times, at any given instant, times the current. Now, the energy, or the work done in overcoming the back EMF, is going to be the integral of the power integrated over time. And so what we have here is the integral of the back EMF, I dt, times I times dt, integrated in this case, we'll call integration variable t prime equals 0 to some time t. But what we're doing is essentially changing variables. And so the energy, or the work done in charging up, well, not charging up, but driving this current through the coil, now our integration variable is I prime, which went from 0 to some value I at time t. This is a straightforward integral, and we just have 1/2 L I squared. And this is the amount of work that goes into taking a current and making it go from 0 to some value I of t. Now our question is where energy is conserved, where did that energy go? And that's what we want to look at next.